Well, I guess it's time to start this evening. If you've been thinking you're coming to the AES session, Graham's told me I've got to stand near his microphone. If you think you're coming to the AES session, you're successful, because this is the AES first session for the year, for 2017. We're the Melbourne chapter of the Audio Engineering Society, and I'm currently the chair, Graham Huon. This evening, we're going to have a look at sound reproduction and how you solve difficult problems. The heading was, what did they say? Maintaining voice intelligibility in difficult environments. So I think you'll find quite a lot to learn from tonight's session. I'll give you a bit of background about Frank, who's going to give the session tonight. Frank has a background in aviation and geoscience. So you'd say, where's the acoustics? Well, he's just a brilliant bloke. So he claims to be an audio dilettante, despite working in the audio industry for over 40 years. He started his life in 1976 working as a bard. That was with the boutique company Burkett Audio Research and Development. Does anybody remember that company? Even Frank doesn't remember it. Making studio monitors and specialist electronics, but was destined for larger sound systems in increasingly large environments. Following many years of concert sound production, Frank became one of the founders of the company's Group Technologies and Quest Engineering. Today, Quest Engineering designs and manufactures electronics and loudspeaker products for the international market and specialises in durable, high intelligibility, I think I need it, systems suited to both physical and acoustically difficult environments, where the wish is for seamless, unobtrusive live sound delivery. Tonight, Frank will be demonstrating an example of a typical difficult and challenging church, where you're trying to get uniform coverage and high speech intelligibility, and to reproduce music and other things, and to show you how you can get solutions to common problems and talk about the technologies, some of the technologies behind this. So this evening, I'd like you to welcome Frank to our session, AES session, and look forward to hearing what you have to say.
Thank you, Graham.
Thank you.
Well, this is pressure, this is, in front of this esteemed collection of audio specialists. Hopefully I won't send you into a coma, and hopefully this won't be geared at too low an intellectual level. But anyway, we're looking at difficult acoustic environments and maintaining voice intelligibility. Now, apart from the fact that that's obviously our speaker system, I'm not actually standing up here to say thou shalt buy a Quest speaker system. What I'm looking at is different ways of approaching the problem of challenged or challenging environments, and because there's really no one-size-fits-all solution. So anyway, moving right along, this wouldn't be an engineer's exercise unless we started by looking at measurement systems. I love doing these sort of things because they're completely. I could never do this at a normal function outside of possibly the gathering in this room. But over the years, there has been a bit of a history behind measuring speech intelligibility. And these days, one of the common words you'll hear is an STI. Now, it's not some kind of sexually transmitted disease or interface or something. It's actually speech transmission index. Now, what we have also, I must mention at the back of the room, is a wireless microphone. Now, should I say something so deeply offensive that an intermediate interjection or heckling is required, of course we have that wireless microphone if someone wants to ask a question or interject or correct me on something in the course of the presentation. But looking at this really, and pardon me if I'm reading some notes here, but the absolute measurement of speech intelligibility is actually quite a complex science. It's potentially complicated by the fact that we all hear differently, and consequently people have approached measuring it from different ways. And what they refer to these days as the STI measures some physical characteristics of the transmission channel, in other words, the room, the electroacoustic equipment, the whole electroacoustic circuit basically, and expresses the ability of the channel to carry across the characteristics of a speech signal. STI is a well-established objective measure predictor of how the characteristics of the speech transmission channel affect speech intelligibility. Well, that was a mouthful, wasn't it? Which is really another way of saying that it measures speech level, frequency response, non-linear distortion, background noise level, quality of sound reproduction equipment, echoes and reflections, RT60 or reverb time, which you all know, and the masking effects of consistent noise and how that's going to impact on the intelligibility of the spoken word. Now, the STI was originally introduced by a couple of Dutchmen in 1971. Now, the Dutch actually, you know how some countries seem to produce an extraordinary number of a certain kind of engineer. Well, the Dutch actually have a terrific record in speech intelligibility in that almost every measurement system extant today comes from Holland. And in other words, some guy started it and then all his students copied him and then off they went, and then they all hate each other and avoid each other at trade shows. So this was constructed to replace longer and more laborious tests. Now, anyone ever heard of the Alcons test? That was quite a long, laborious test, but does anybody have the Don Davis book? Don Davis, Sound System Engineering. Okay, that's he was a big Alcons man. But anyway, but basically what they were trying to do was come up with a system that could get rid of everyone sitting there with a notepad and listening to 4,000 words coming through a sound system or by a person speaking, and then writing it down and working out what percentage they could understand. What they try to do is kind of automate a system. Now, the test now, there's a thing that they refer to as a RASTI test, which really is, I think it was what RASTI was this is a ripper. It's called Application of RASTI to Transmission Chains Featuring Electroacoustic Components such as loudspeakers and microphones became fairly common and led to complaints about inaccurate results. Okay, well, what's happened with some of these tests is, of course, there's quite a few of them now that essentially are trying to replicate that system. And what happens is rooms that everybody agrees sound great tend to not pass. But anyway, we'll get to that. Essentially, you've got Alcons is the kind of the test that was most popular in the USA, and then you have the STI, which was common in Europe, and then of course there's another one called a C50, which is a clarity index, and some people would say, well, what if you're going to test for intelligibility, what is the best test? Well, there's probably no clear answer to that. The initial, and of course no tests ultimately gets used for how it was originally designed. The Alcons test essentially was a predictive tool. The STI was used as a measuring method, and the C50 was really intended to determine clarity. Well, of course, C50s, which was quite a good test and probably the most likely one that would actually give you a real prediction. Prior to looking it up on the net, I'd never heard of it, so that's how popular that is. The STI has really become a predictive tool, and the Alcons has become a measuring tool. So they're all basically it all turns around. So then somebody turned around and decided that they would work out a program which is on the net where you can plug in your Alcons measurement and it will give you an STI, and then you can have an STI measurement, it will give you an Alcons. But essentially, if you have a look here on this scale, it gives you a bit of an idea that anything getting approximating 1 is good, and anything that but basically, sorry, that the STI is likely to predict the syllables, words, and sentences being comprehended, and of course the common the CIS scale is based on a mathematical construction of that. So sometimes you'll see STI and CIS used together, but they're kind of interchangeable. One is a mathematical construct, and the other is actually a measurement. So in the case of Alcons, you have a percentage measurement. So something that's at 3% is very good, which means you've only lost 3% of the consonant values. And as you drop down the scale, of course, you have higher percentages. Now, bearing in mind, they all originally came from live tests, which was done with a room full of people sitting there, and they would have a speaker or a pre-recorded quantity of random words, and people would sit there and they would write down the word that they thought they heard. And at the end of that, the score would be calculated across an average of the quantity of people were there, and that was originally your Alcons measurement. Now, during the 40s, there were, of course, Bell Laboratories became very involved in trying to come up with a measurement system that everybody would use, because by then they were building sound systems and putting them into buildings, and they were trying to really work out a way of maintaining some kind of design tool. And so a lot of things came into existence where they tried to come up with scales. I found this one on the net a few years ago, looking at old style tests, and this one's sensation units. Now, I'm not quite sure what a sensation unit is. I've trawled every possible book and everything, the possible exception of porn websites, to find out what an engineering classification of a sensation unit is. But at one point of time, Bell Laboratories did go down that path. So essentially what we now have is most of this isn't done with people reading from microphones anymore. It's done with measurement systems, and of course there's an ISO standard which gets reviewed about every 5 to 7 years, which the people who make the test equipment love, because every 5 to 7 years you have to buy a new one. Now, some of them are Buell and Kahler, I think, manufactured essentially a type of software system, but you still had hardware that you had to buy to make it work. They were kind of the first, and the RASTI values were really conceived in a form of making it possible to have electronic measurements. So Buell and Kahler came out with the rapid speech transmission index meter. They were the first people to really do it, which is what the RASTI system is essentially based on. And you would have, I think it was values above sort of 0.75, 0.8 were good, which still meant though that you were losing 20%. So I don't quite know how they think that's good. But anyway, that was but that was basically what they had. That essentially became a standard measurement system, and then other people started making one. This one is by NTI. Now, NTI quite good because we actually use an NTI QC system. And I don't know if anyone's ever used an audio precision machine, the AP. That's an American system which was for many years a standard for certain kinds of audio measurement. And that was an American system, and being American software, it was a bit clunky and complicated, but it actually did work very well and did certain kinds of measurements if you're designing filters, and it was really good. Then NTI came out with a whole lot of measuring stuff, and we bought their QC system where you can automate the QC process, and that was very impressive. But they also made this kind of modulated, I think it measures a modulation transfer function. Now, most of these kind of RASTI measurement systems are based on what they refer to as a modulation transfer function across 7 octave bands. And the basic principle of them consists of emitting a synthesised test signal as an alternative to a human voice. And the speech intelligibility measurement acquires this signal and evaluates it as they believe would be perceived by a listener's ear. Extensive investigations have involved the relationship between alterations of speech characteristics and the resulting speech intelligibility as interpreted by the machines. These findings are incorporated in the speech intelligibility meter is able to display the intelligibility result as a single number between 0 and 1. So it kind of falls into the STI kind of index. So basically what we have is a whole lot of measurement systems that, for the purposes of compliance to a standard, ultimately, when you look at, well, who's going to get paid and where are these things done, it's really railway stations, airports, commercial environments is really where these systems kind of excel, because you also have masking noise. And the great thing about especially systems like the NTI, you can do the measurement in situ over about a 15 to 20 second period. It just does a sweep and it sends some pulses and does some other stuff. So you can have everybody standing there waiting to catch the train, and then you can run this thing and you can do a real-time test. Whereas the Buell and Kahler one, they've got a system where you have to synthesise the background noise. So you have to go there during the peak period, you have to measure what the noise is, and then you have to wait till everybody's gone, you have to play that noise back as a masking noise and then run your test. So a little bit more cumbersome and clunky. But ultimately all of these systems are really just good for getting paid if you're installing a sound system in a Olympic swimming pool stadium or something. When it comes to doing venues, dare I say, probably the best determiner of does it work is showing up and having a listen. And can I understand what's being said? Now, in the Don Davis book, back in 1970-something, I think, when he wrote it, he talked a lot about reverb and the influence of reverb on speech. And when you look at all the measurement systems and the way they work and the history of them all and the whole thing, the big common denominator of them all on intelligibility degradation is the reflective nature of the reverberation time in a venue. Like the reflective nature of the venue and its contribution to the reverberation time and the frequency of the reflections. And we can, I don't know if anyone here ever had to work much with architects or do sound system design in buildings. Do we have any architects here? Oh, it's a relief. Look, I think we can pretty much assume that the ears are painted on. And after having dealt with a few of them, I sort of started to feel that the purpose of the ears was to hold up their designer glasses, and that really, that they've come up with their design for the space. It's not a room. It's not an auditorium. It's a space. And so you come along with your sound system, bing, 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 clang, and they're hyperventilating with horror that this is going in their space. Now, they never answered the phone when you were trying to get involved during the formative design period, like, we're going to need a beam here because that's where we need to hang the PA and whatever. And the other thing is, of course, these days they have the advantages of computer-aided design, which really, really should be something we could get quite enthusiastic about, except that I've never seen a sound system in an architect's drawing of a room. Computer-aided design, and they know they have to, if it's let's say it's a bar, they know there has to be refrigerators. They know there's got to be toilets. They know there's got to be an exit sign above the door. There's got to be a whole bunch of things. But as for a sound system in your auditorium, no. Now, so, and you could ask yourself, is this a phenomenon that is a 20th century phenomenon? Or maybe isn't it? Now, auditorium, Latin word for place of hearing. Now, we think of it in terms of the Romans, but actually, really, we know the Romans as great rip-off artists and commercialisers, and that the real people who tackled this were the Greeks. And you go back to the early Greek approach, the democratic approach. And if you're going to run a democracy, you've got to be able to talk to people. So if you're going to talk to people, you've got to have a place where you can put them all and where one person can stand there and talk to everybody. So they had a pretty, a political requirement to solve the audio problem quite early on. And when you look at it today, we use loudspeakers and microphones and all the other stuff, but they actually had to solve these problems just with someone speaking. Now, I'm going to come back to this in a minute, but bearing in mind that the Greeks are also great mathematicians, you could go and look at, say, the Greek amphitheatre, and there's any quantity of papers that have been done on the Greek amphitheatre. So if you're stuck for a doctorate subject, go to Greece. Sit there and with a LiDAR measuring laser or whatever, and come up with your take on why this amphitheatre works so well. You see now. Okay, so the relationship between Euclidean geometry possibly and the amphitheatre, but we'll get to that. Trivia question: when was the first published work that focused on acoustics for the purposes of understanding the progression of sound waves? Any idea? Yep. No, that's good. That's good. Got to run back a bit further.
38 BC with Vitruvius.
That's yes, but I didn't actually want to go that far back. I'm thinking more published work that. And I'm coming back to that point. The first published work, essentially, by modern times, I'm talking, Renaissance or thereabouts. As soon as I can find my little place on the screen here. Okay, now we're talking 1657, and we're talking a guy called Gaspar P. Giotto. Now, as much as he did this in Italy, but in actual fact, he was an Austrian. Now, Austria and Italy have interchanged borders from time to time. So, Gaspar was the first person in modern times to approach the propagation of sound as a geometric problem. And he also, I think on the illustration, we've got illustration reflections of sound wave behaviour within a semicircular reflective environment such as under a dome, bearing in mind they were building plenty of domes in Italy, what's it called, the Pantheon, etc., etc. So they had plenty of areas they could measure it and write down some geometry, or within a parabolic stone wall. Whether a person shouting or an amplified speaker of sound wave will behave the same way, and the reflective surfaces will greatly affect the sound, especially if the listener is in a position where they'll hear more reflected sound than direct sound from other sources. You see, now, we look here, a graphic representation of the rules regarding reflective sound expresses a geometric problem. That's Gaspard, because that book still exists. It's in, I'm guessing it's probably in the University of Barcelona or something. Applying the principles he had developed, Gaspard looked for practical applications. Because we're sort of talking about the times of the Medici and around that, and there's a fair bit of money to be made if you could help the rich get richer. And he even developed a listening system for spying. His bugging device was a horn and reflector that could be rather hard, it would be a bit hard to hide, but if you didn't know what it was, well, you just could stand in front of it. A post-medieval mechanical sound featuring a large horn to direct and amplify speech and music. Staying with the history of venue acoustics for a moment, let's look at how the purpose of this building and the style of performance affected acoustics at the design stage. And of course, he was looking, he designed a thing where if you put your ear in one place, you could hear what they were saying on the other side of the square. On the other hand, he also worked out ways where if you stood in this particular part, you could also address the masses. It's kind of, his idea was kind of a reverse of the amphitheatre, because instead of standing here with your wave being focused up to the bleachers, and bearing in mind that even down to the type of stone they were using and the shape of it had a masking effect to lower the bass content to actually maintain articulation. It is said that they had large vases or water containers in strategic positions, and depending on the performance, they filled it to different levels of water or ash, consequently had Helmholtz resonators all over the place. So whether it was to give someone an amplified bass, big present voice, or whether they wanted to make them sound a little less impressive, they could move things around in the amphitheatre. So what Gaspard had was the reverse idea, was he was on the parabolic wave trip. Now, if we look, going back to Graham's friend, there's Polyketitos, I think his name was, the younger, Polyketitos the younger. Audiences in this particular space were estimated to have been up to 14,000, which is pretty significant. And as I said, there's been numerous modern day evaluations of this. That was pretty good, but with the Romans' capacity to rip people off, rip off good ideas, the Colosseum, what we're not aware of about the Colosseum is they used to have ropes across the top of it, and they used to have these blinds that they could draw that pretty much covered large sections of the Colosseum. Now, people thought that that was just for shade, which it probably would be. That could get pretty hot after a day of, hungry lions and chariot races. But also, somebody sat there and modelled it with the linen top and realised that it could also act as a sound containment device that, depending on how you spread them out, could mean that you could stand at one end of it where the emperor would be and talk, and that wave would actually reflect quite nicely around the space. And on this particular amphitheatre, they've also found little holes in the stone that they were trying to work out, well, what did that do? And they worked out that pieces of wood could be in there, so they realised there's probably a whole lot of bits of this that obviously we can't see now, but they suspect when they've modelled it, that same thing, that there was actually the capacity for reflectors to go over the top of it. So anyway, now we've moved to the Gothic church. This is... now we have to bear in mind, for anyone who's to put a sound system into a Gothic church, that is just everybody's nightmare when you get to do one of those. And you go, what were they thinking? Now this is a picture of Cologne Cathedral, which was took 500 years to build. Now, if you were the family that got the contract, wouldn't you be toasting great-great-great-grandpa every Christmas time when that came around. They took 500 years to build it, but it is a stupendous building, and as much as it was renovated by the RAF in 1944, it was not that hard to put back together because it was so well built in the first place. But that has got to take an award for the most hallowed reverb time in the history of architecture. And we look at it and you go, why? What is the point of that? Because we have to remember that when these churches were built, they weren't trying to be the Greeks anymore, where it was friends, Romans and countrymen, or the Romans. What it was a chanted or Latin mass. And in most of the places where these were built, the only people who spoke Latin were the clergy and the intelligentsia and anybody educated by the Jesuits. So consequently, nobody knew what was going on. Consequently, you had the bishop and the priest walking down, waving the incense, so that he didn't have to suffer the vapours of the great unwashed as they walked through the crowd. But the point being is that it was for a hallowed experience. They would go there and there would be this atmospheric, and it was to largely reinforce the power of the church and the hierarchy, and to give it a depth and gravity to the mass, essentially. Now, that model has lasted for a very long time. Even in the 50s and 60s, when you had sound systems, they were still building takes on that, only made even worse by the influence of postmodernism. So consequently, you had possibly some of the most potentially unintelligible spaces known to man designed around that time. But if you move into the present era, and we'll call the present era in 1915, because by then you were starting to get amplified sound systems. And if you look at this picture, that's quite a spectacular crowd. I don't think that's 1915, I think that's about 1922, but you can see by 1915 they've gone from a very basic horn speaker to quite a sophisticated array hung on wires. And then, of course, from that you jumped quite heavily into the cinema world. You can see my little homage to Western Electric there, and Altec, who pretty much invented everything at that point of time. Now, we'll get out of that and we'll move into the present era, because ultimately what we're looking at is how we deal with sound in modern spaces. I'm finally getting to the punchline here. Now, when we look at the present era, we have a variety of rooms built by a variety of architects. The rooms are all of different age, different influences. Some of them have to be multiple purpose, some of them are very specific in their design. And in the last, let's say before 1990, you still had a strong effect by I could call them the old guard Altec approach, which all had the point source type system where you'd see a row of Altec horns in the middle of a room. Worked quite well. Anyone remember Dallas Brooks Hall? The old system that was in there. I remember years ago seeing a Cleo Lane concert in there, and it was fabulous. But not that long after, I think they ditched that system, because people coming in wanted a stereo sound system. Now, what was in there was a perfect sound system for what that space was, and was pretty appropriate for the kind of performances they had in there. And they had a mixing console up in the bio box. They had big Bakelite, knobs on. I think it had a bass and treble control if you're lucky, and a clang, clang, clang input gate, and a 48 volt transformer that hummed, the whole viso. And that was a terrific solution. And that was those sound systems that were designed in those days. They were pretty much custom designed for the the venues. But due to the fabulous range of product that Altec made, you could just go and sit there and you could just design up with a pencil and paper and a drafting board where your horns were going to go and what coverage was going to be and how loud it had to be here and how loud it had to be here, and you'd go in and you'd do a sweep test and it would all work, and it was fantastic. But eventually when we got more hi-fi and we wanted full bandwidth sound, and then they started hanging everything from 4560s and A7s through to all kinds of things that didn't perform as well, but they made a lot more noise. Now, present era, here's a little example of a room. There's a church. I've picked churches. I'm using churches a lot here because there's a lot of them. They're generally, some of them are very elaborate and have got a lot of money spent. Some of them are not. They're generally built by, dare I say, enthusiastic amateurs that have seen another church and they want one of those. So that they come along and they build a church, and essentially the reason that I've dragged everybody out to the Antipodes here is that this is a great example of a modern church, 450, maybe up to 600 people. There's actually delays outside. You can actually go out to the front door and it is actually all time aligned and everything. So, and in a church like this, they'll quite often have something where they'll have people out there too. So, and they use it for all sorts of things, as most of these kind of churches are very much geared to a community general use sort of situation. So they've got to do everything from reproduce spoken word, and in your average church you'll have varying degrees of sophistication in the operators too. So they'll buy something that they've seen someone else, or there might be a guy who's a professional sound guy who's a member of the church, and essentially they go shopping for something that everybody else has got. So there's an example, right? Here's another one. Here's another sound system that you could find in a church. And here's another one. Now, I think before you put this one up, you would have definitely waited till the architect had gone. Now, anybody notice any common denominator between these? In that they're all line arrays, you see. Line array is the big thing. Sorry, I'm changing mine there and you're not seeing the change, all right? Line array, line array, line array. It's as what was when they had a consultant in here. The consultant said, "Oh, you need what you need is a line array," and they spec'd a line array. Let's say that's pretty much these days the first port of call. Now, I'm going to get stuck into line arrays a bit, but not for the reasons that we don't make a line array. The reason we don't make a line array, there's plenty of them out there in the world, doesn't need another one. Now, line arrays have a lot of advantages and are a specific tool designed to solve a specific problem. And the great thing about line arrays, in theory, is that you can have predictive software that, so long as you draw the room in right, the predictive software will give you a pretty good estimation of what you're going to get. So they're very popular. Now the question is the hype justified? And like the measurement systems, which are horses for courses, so are the speaker systems. Now, should we or should we not have a line array? Now, I'm sorry for probably all of you, this will be a little bit boring because you'll already know this, but I'm just going to go over this very quickly. We're just going to jump back to our friends, the inverse square law, for a minute. Now, we all understand the inverse square law, and we've got a ratio of change of one or more unit less in quantity will double the result. In other words, when we apply an audio noise source, if you double the distance from the noise source, you have 4 times the decrease in volume. The effect of the change is called the inverse square law in level. Changes in acoustic power to measure in 3 dB. Okay, now I've got that out of the way. As we see, from the above chart, 120 dB at 1 metre is only 86 dB at 50 metres, 165 feet. It's a relatively short distance we've dropped from the threshold of pain to barely above normal conversation. Now, the reason for that, as no doubt everyone here will probably know, is it's the nature of the expansion of a wave is going to expand like a theatre. Like the light bulb in a room, you switch it on and it goes everywhere. Now, that's what is the accepted wisdom. I don't necessarily think that is completely true when it applies to a sound system in even a conventional array, but let's pretend for a moment that it is. And if it's not true, it's not that far off true. Now, when we want to get to, say, a room, you put 2 speakers up, fine, it works and noise comes out and it goes a certain distance, and due to the inverse squared rule law, it all falls off, and at a certain distance it's not loud enough. So in the past our solution was to put up another pair of boxes, so double the output. And consequently you get more noise, but you also get more of a lot of other things. And as you can see here, by just 2 speakers pointing into the same space, we have our little array, and you can see that we have tangential waves crossing each other. And sorry, you might need to do that again. You might, So we have our tangential waves, all right. So, and depending on the distances that are involved, we're going to have comb filtering at certain distances. And in the old days in doing live sound, when you had to put up at a concert, we used to try arraying them so they all went in the same field and this sort of stuff, but when you got to a really big show, the standard type of thing that was available, there used to be a product called an S4, which just was a big cluster of drivers all pointing forward. And we used to say put up 1 or 100, because we found that if you put up enough of them, all of the effects kind of went away because there was so much comb filtering that suddenly you could then start equalising it again and it would be all be fine. Now, the principle of comb filtering gets back to this concept of the interference effect of tangential waves. Now, I could use a practical example, because what we really want in an array is it just to behave like one box. We just want the sound to come out. We don't want any tangential waves. We don't want any interference effect. We don't want any comb filtering. We just want a wave to go out into the room. Now, once you have a bunch of speaker boxes and you put them next to each other, the single box is like throwing a brick into a pond and you see this nice wave emanate. So that's a 2.5 kilo brick. Now you pick up 2.5 kilo of gravel and you heave that into the pond and you get all these little wavelets. Now, if you had a little floaty on the side of the pond and you were measuring the wave energy, and then you threw the gravel in and you're measuring all the wave energy, once you got to the end of the first collection of waves and you total it up, you'd find that there was actually quite a loss of energy across the whole wave. Like you'd have a big energy loss. And what is effectively happening is with this these tangential waves, is we're getting what most of you will know as obviously as a comb filter, like this. So it's not like that anymore. We got this going on now. The real purpose of the comb, our brains are designed to interpret a comb filter as location in space. That's, you know how we have ears on both sides of our head, except architects, and what you have is the time delay between your two ears. There's an area in your brain that synchronises that, and that delay and that filter effect is actually how we determine location in space. So a comb filter is a good thing when it's in open space, and when you're getting reflected sound. All those sorts of things are information that, on a fairly unconscious level, we are translating into information we can use. Like the lion is that way, so I'm going this way, you see. So helpful. Now, when we listen to audio through a electroacoustic circuit, which for us as the human species is relatively new, and there's comb filtering going on, we're listening to the music, but on a very unconscious level, there's a little unresolved bit of processing going on, a little unresolved feedback loop going, what's that comb filter? And it actually sets up a form of stress. Now, some people would see that as an unnaturalness, some would see it as a form of aggravation that's at a very subliminal level. But soon we dismiss it. But it is a little source of stress there. So the other problem, of course, with comb filters, and what we have in this graph is we have a frequency response of a box, and then someone switched on a box next to it, and what you have there is the comb filter. Now, what's happening is that can't be equalised away. You can't make a processor that will get rid of that. It's just going to be a form of distortion. And of course, the more speakers that you put up, the more of that effect you're going to create. And of course, depending on the crossover point in the boxes and a number of other factors, it can basically get considerably worse. And of course, what I have here is a graphic representation of a phase shift, which of course is, as you will know, how a lot of equalisers will work by changing a slight phase shift at different areas of the frequency spectrum, and it will create little filter sections. So there's a lot of filtering going on that was not within the intention of the designer, who in his optimum room where the product was designed, he's listening to it in a way that it's probably not going to be heard when it's going to be used. So we established that we can't equalise that out. The more boxes that we use, the more of the effect happens, and consequently we get back to the old S4 principle. Now, what I have here is a vertical view looking down on a two-box plot. I call that the Christmas tree. Now, there's really, as you see, that's lobing. Now, that's lobing quite heavily. Now, remember that picture, because when we start talking about line arrays, we're going to come back to that. That's in a two-box array. That's a pretty bad one, but it's not that out of order. I've actually seen line arrays that were close to that. So now we move back to the line array. So the line array really was a solution that was introduced about 25 years ago. It started to come about to solve a particular kind of problem that was existing in certain kinds of concert venues. Now, by line array, what we actually have is a line source. Now, we had our spherical waveform we're talking about from our point source type system. What the line array is trying to do is create a cylindrical waveform as opposed to a spherical waveform. And you can see by segmenting the spherical propagation model, we're stuck with a 6 dB loss in a conventional cluster of boxes. Whereas when we start stacking the sound sources on top of each other into a vertical array, something happens to our spherical model. With a tall line of transducers, the wave emanating from the lines, it becomes what they refer to as a line source instead of a point source. Where this is quite useful as a predictive tool is a highway. You'll notice how annoying is highway? You get a straight highway, road noise, you have a line source of a whole lot of noise. The noise seems to go for a long distance. So it's not that it's noisier, it's just that the way the wave is propagating from the road is such that it's able to carry a long way. If you're up a hill looking over the road, it's going to be quite loud. Now, the line array, or the early work on this, was done by a gentleman by the name of Harry F. Olson in America. Clever guy, held something like 100 patents. He was the guy who figured out that it was observed that a single vertical array of acoustic radios produced increased directivity in the vertical plane. And it's got, I've got old early line source boxes can still be seen in many town halls and public venues. They are much smaller than a horn-loaded system and were found to project the voice-speech area well. You'll notice that most of them were not big drivers. It was a long row of little drivers, quite often actually 100-volt line speakers put together, and without having, you get your good old Toa 20-watt valve amplifier behind it, going into a couple of 100-watt Toa about this long, or made by AWA, or made by a few other, Vitavox or someone, back in the day. Each speaker was about 4 watts, if you're lucky, and the thing would cover 1,200 people. In fact, I think the Melbourne Town Hall used to have something like that many years ago. And by directivity we mean the degrees which the wave is directed to narrow and to a more directional field of coverage. So Harry F. Olson, he was the guy who started that. Now, it worked really well in the kind of voice propagation area, and because now we had an expanding cylinder and we're only losing 3 dB per doubling the distance, it made it a tremendously effective way of projecting a wave across the room. And when you look at your old shoebox town hall, you've got your boxes hanging up there and pointing into the people and not to the walls and ceiling, and due to the directive nature of them, and they ran out of gas at about 120, 150 hertz, maybe even a bit higher, their intelligibility was actually surprisingly good. So what the question is now, of course, is what happens to a line array in the real world? Now, for example, in here they wanted to specify a line array, and the system that they had selected, apart from the usual issues that you have when you put them up in a church and that they're big and you've got to hang them on the right place, and you've got to have something structural, whatever, a real line source line array has to be a certain length before it's going to project a cylindrical waveform across it. And that length is we're back to quarter wavelength theory again. It's got to be a certain length before it's going to be a real line array. The second thing is it has to be tangential, like it has to be non-tangential across the whole frequency spectrum that it's projecting in. So as soon as you start getting the line array is too short and you're starting to get tangential waves coming out of that line array crossing the next element, you are going to have that Christmas tree back again, and you'll have lost the actual the effect. So realistically, these worked great because they were only a narrow band of frequencies, and all the areas that were trouble were outside the range of the box. So what Christian Heil did, now Acoustics was the company that really popularised the full bandwidth line array concept. He was a Frenchman, and consequently something like this would have to have a Frenchman, because nobody was going to believe it in the days when bigger was better and you had the big wall of doom, to then come in with this little sound system that you're going to hang and try and convince people that that is somehow better than the wall of doom. Only a Frenchman would probably have had the persistence to stick with that. But he developed a type of diffraction device and process that would give you, that would minimise the tangential effects across the widest range. It wasn't across the full range, but it was across enough of the full range. Now, the other reason for doing this was in concert sound, when you'd have your big wall of doom going and you were outdoors, and especially if you were in a humid environment, there'd be a couple of problems you'd run into. One significant problem would be that you would, the top end would largely be absorbed by the air. So as you got away from the box, it would start to lose that and then it would start to lose parts of the mid-range, because bearing in mind, parts of it are behaving like a line array, because the good old S4 had a row of speakers down here and a row of speakers down here and a row of speakers down here, all in the one box. Now, if you stacked them, you did get a kind of a line source effect. But what you also got was a tremendous amount of lobing and a lot of other issues. So, and you couldn't focus the energy where it was required. So once you had your cylindrical waveform, so you've picked up quite a few dB, especially if you're a reasonable distance from the box, but that laser effect that you got in the top end meant that that top end would carry a significant distance without destroying the hearing of the people in front of the system by being ridiculously loud. So he came up with that system, and then from there everyone was jumping on it. He also came up with a predictive software system. So that was a big change. It didn't take long before everyone was hopping on the bandwagon, but because people didn't have the patent that he had, they had to try and come up with other ways of making it look like it worked, or come up with their own. And that turned out to be a lot more difficult than it appeared. The VDOSC was essentially the Acoustics line array system that had that terrific coherence and projections in the mid-range. Well, once you get down to the bass, it wasn't a line array anymore, but that didn't matter because, as you know, a bottom-end wave will just keep on going because that's where all the energy is. So he could then sit there and the other deal that he did, which was clever, you couldn't buy them, you had to lease them from him. And then he had to, being a typical Frenchman, to decide whether you were sufficiently professional and rich enough to afford his system and whether you were going to use it properly. So he did the training, he decided who was going to get it, he made sure they all had the modelling, and consequently, from the early days, they were getting great results. So then it caught on after it became a must-have. Now, the way these software systems work, of course, if you just put it up in a straight line and point it at a crowd, you're going to kill the people in front of it, and the people further away are going to get probably a nice sound. So then they came up with the concept of trying to shade the array. The difficulty that they then ran into is it doesn't quite work to just turn down the bottom boxes, because then you have pressure gradient differentials from the super loud ones to the super quiet ones. And of course, what happens when you have a pressure gradient differentials like high pressure and low pressure? The wave starts moving around. So that started to develop, to break down the cylindrical component of the waveform. Then they came up with the idea of just having wider dispersion boxes. So in front of the box, the boxes at the bottom of the array, instead of being, say, 5 degrees, became 15. So they had the same amount of energy coming out of them, but you just had them covering a wider area. So that made that kind of a bit more bearable and maintained the integrity of the system. So basically what they ended up with was reasonably even coverage. In terms of real line array, it kind of was, but kind of wasn't. But at that point in time, Acoustics were the only people that had a real one. The only other people that had a real one was Adamson, because they used a VDOS type system and paid Christian Heil a royalty. Then another Frenchman by the name of two Frenchmen, Eric Vincenot and Francois Defrague from Nexo, in 2003 came up with another system. Now, I don't know about you guys, but I remember years and years ago saying JBL used to have a horn that you used to get, and it had this massive driver, and it had this long kind of horn throat, and then it curved around into a sort of a mouth, and it was sort of a biradial kind of horn, but it came up this pipe, and
it sounded quite a lot like this if you wanted to simulate a 75 RPM record.
well, that's what you used. And the idea of it was so they could fit it into a small box. Now, it was absolutely horrid. And I think everybody that heard one, it completely turned anyone off the idea of anybody that's trying to bend a wave, because you could just imagine the phase relationship in that wave by the time it's turned 90 degrees and come out this fairly incoherent. You could tell it was designed by someone who was in the art department. It certainly wasn't designed by a designer, but JBL put their name on it and probably sold a whole stack of them, so they didn't care. But the thing was that every time I saw anything with a wave with a device that bent, I'm going, nah, forget it, not going to work. And then different people were trying to fit, when the EV had one, MT4, and they bolted 4 drivers onto this massive horn, and they had this really complicated looking phase plug arrangement, and you stood out the front of it. It was like an instrument of torture. Like, it was insanely loud. You could have had noise complaints 5 kilometres away, and then of course they had this processor for it that had filter settings that I think even the late Neville Teal would have looked at and just laughed. It was full on, and even then it kind of worked. It was certainly loud enough, and let's face it, the music they were playing in those days was nothing to get excited about anyway. So it sort of worked. But every time I would see anything with multiple drivers or that had any sort of junction involved or any sort of bending wave, you just look and go, nah. Then Nexo brought this thing out. Now, what this worked off, I looked at it and I thought, oh God, not another one. And then I heard it, I thought, that's got all the top end for days. You could put an orchestral piece of music on. It didn't sound like a PA. It sounded like a hi-fi system. I'm thinking, what have they done? They said, and what they had done, that they had a driver that's, the drivers in this thing for the HF are parked around the back of the box, sideways somewhere. And you go, how did you do that? And how are you bending it? We are not bending the wave. We are reflecting the wave, you see. And I said, well, how does it work? And in the end, what I got to with this was pretty clever, because you've all, anyone who's been past the radio telescope at Parkes, for instance, you've seen the big telescope at Parkes, on the dish. Well, you see a big radio telescope, you think, okay, it's a reflector, right, whatever. But how that works, they just don't point it and go, oh, a little micron to the left, there's that star there. That panel, they can switch bits of it on and off. And by switching parts of the reflector on and off, they can really narrow that beam to pick up a very precise point in the sky. So what they're doing is it becomes a shaped reflector to give you a very precise point. And what these guys had figured out mathematically was that the best way to control the wave, because what they were trying to do was have a row of lasers. Now, you take a pin spot. If you put a row of pin spots together and shine through the air, eventually you'll see them start tangentially intersecting. And realistically, that's what happens with all the line arrays. Even the VDOSC, you get to a point where the wave starts to drift and they start crossing, and you start getting lobing and you start getting a bit of interference effect. It's pretty good, but it does happen. And what these guys had figured out is if they sent a wave to a reflector, shaped that reflector, and then sent that down a type of a diffraction slot, they could very, very precisely stack these and create a totally authentic cylindrical waveform across that frequency spectrum. Then they worked out, if you look at the shape of this thing, it's got these little sort of look like vents at the front. That's a cone displacement device. Because, of course, the other problem when you see line arrays that don't have this kind of displacement is once you line all the cones up, you then run into your quarter wavelength problem again, where the crossover frequency is in the case of the top end, where they would have the problems, below a certain frequency, they cross it over before you get there. You can do that in a top end driver, but you can't do that very easily in a bass driver. So you end up with your quarter wavelength, once again, tangential wave problem, and you end up with a bit of Christmas tree at that end of the frequency spectrum. Well, the whole concept of that cone displacement is it turns, because that's a row of 8-inch drivers, but the cone displacement turns them into 4-inch drivers. So where that would have a problem is actually above the frequency area where that's crossed over. So pretty clever. That would mean that at that array you would have a very cylindrical waveform. Now, the only problem with that picture is that the line array is not long enough. In actual fact, for that to really work, you have to put up 32 boxes. And you know how much they are? How much do they cost? $22,000 each. $22,000. Can you imagine? French, what were they thinking? So, yes, but we have got the best one. Of course it is expensive. This cost us a fortune to develop. And in fact, when Nexo developed this, to test their mathematical model, they couldn't make the device that had to do this. Nobody could. The only way it could be made was on a 3D printer. Now, in 2000, when they were developing this, or 1999, whatever it was, there were 2 3D printers in the world. One was owned by the Jet Propulsion Laboratory, JPL in America, and the other one was owned by Mercedes-Benz. They had the third one, and to buy it, they had to publicly list the company and virtually lost control of their own company in order to buy a machine to test a mathematical model. Now, I've got to say, French or not, that is commitment. So anyway, they developed that and it did work. And first of all, they tested in a straight model and then they tested the reflector. There is papers on this. I think I've still got them. They used to be on the net, but they've since been withdrawn. They're a pretty interesting read because in that paper, there is everything that's wrong when you try to set up an array. Because technically, to maintain a consistent 5-degree output, you have to have an infinite sound source back at this end. It's a bit involved to explain. I do have a presentation on it somewhere, but I actually can't find it. But if I can, anyone wants it, it's a stunningly fascinating read. And with that idea, we actually took that and started to use that as a little bit of data parked up the back here for doing conventional arrays, but I'll get to where that comes in later on. So here we have, there is the downward view of the pattern coming out of this geo system. I haven't seen anything that gets close to that across the bandwidth that's being measured across. And now, having said that, I'm sure the only time they ever got that's in the laboratory because some of the best sonic results I've ever heard were through that system, and some of the worst sonic results I've ever heard were through that system. And this is where it falls down, is when they would have to set it up. Number one, you have to put up 32 boxes at 22 grand each if you want the full effect. Number two is you have to set up each box with a laser. Now, can you imagine what road crew or roadies are going to sit there and climb up the array and set everyone with a laser? What is the chance that's going to happen? 32 boxes aside, 64 boxes. Are we dreaming or what? So consequently, the idea never really caught on, because a lot of people bought it, because we all went to the demo and we were blown away, saying this is the greatest. Nexo probably hold more patents than everyone else put together, but half those patents will never see the light of day. For those kind of reasons, we thought this is the greatest PA in the world. Everyone else is toast. And then when I went to the shows, some of them were just abysmal. So we're back to the problem then. It's a lot of the problem in getting results are who's putting up the PA and where is it being put up. We're back to the room. We're back to the room reverb. We're back to where you're going to hang the PA. We're back to real-world options, because no one's going to spend $22,000 an element on the rig. Now, apart from the good old line array, there are other ways of doing it. There's delayed systems. Now, I've got a whole thing here on how to do delays. I'm not going to bore you all with that. I'm sure you've seen all that before. But delayed systems can come big or small. There's actually a delayed system out here, those little boxes. They don't have to be a big sound system to use a delay. Likewise, big sound systems can greatly benefit from running a delay. The trick really in running a delay is a thing called the Hass effect. And another problem you have when you're installing a sound system and you are going to use a delay, and you're going to use conventional speakers. These are technically a conventional speaker, but they're not, but I'll get to that in a minute. When you're running a delay, really, quite often you don't get to hang the delay boxes where you want to because of architectural considerations. So essentially, if you pace it out, your good old 1200 or 1160 feet per second at standard temperature and pressure, it's the old count a foot a millisecond and then add another 20 milliseconds, because the Hass effect, there's actually papers on Hass. He was actually it's a pretty involved set of papers he's put out. But essentially, when you look at the human ear, anything we can't resolve more than less than about 20 milliseconds. More than about 20 millis. Sorry, less. And if you are setting a delay and you pace it out roughly and you add 20 to 25 to 28 milliseconds, the first wave that hits your ear will be your perception of where that wave's come from. So if you've got a sound system over there and then a pelmet and then a whole lot of stuff and then a balcony and something else, and then here a couple of little speakers, and you bang 20 milliseconds to 25 milliseconds on that over the distance, the great compliment you'll get is people come up when you're twiddling the knobs. They go, hey mate. You think, I know what this is going to be. Hey mate, them speakers up the back, mate, they're off. The speakers are off, mate. You go, oh, it's all right. Can you hear the sound system? Yeah, mate. Good. Better I'll leave them off then, So basically, what you have is well-timed delays are actually invisible. The other trick is, of course, is that you don't want to turn them up too much, because then you will have more comb filtering and you'll have all the other, action and adventure. Anyway, I've got a bit about delay times and that, but I think we can just shoot past that. Reverb, we probably don't need to talk about that to a great length. You all know what reverb is, and early reflections and what have you, and RT60 being how long it takes for the sound level to drop 60 dB. Critical distance, that's a good one. Now, when we have our, whether it's a line array or our conventional array, we're back to the issues of room reverb. Most buildings, you've got a stage like this and you've got a couple of speakers either side. In some places you might end up with a bang one right in the middle, and in some places you might even have some little fill boxes along the front. Now, your boxes sticking out are going to hit a wall in the ceiling. Now, for example, in a room like this, line array or to not line array, whatever you do, wide dispersion, narrow dispersion, whatever, a narrow dispersion box would focus the energy into the room. It would clear the walls and ceiling. It would give you a lower reflection, but then the people out the sides aren't going to hear it that well. So you're going to have more boxes. And then they're going to be a bit too loud, so you've got to turn them down. It turns into a bit of a process. Then you've got a whole lot of stuff up there. Now, critical distance is the distance, the place in the room where the reflections and the original sound are at about the same level. And once you go beyond critical distance, we're back to the Alcom's percentage index. What are you losing? And as you'd be no doubt aware, vowel sounds are strong, consonant sounds are weak. You start losing the consonant sounds, and it's like, what did he say? What did he say, dear? And if I'm a bit deaf, and I get to places and if I'm not hearing it at all, I start to vague out and lose interest, because you only really need to lose about every fifth or sixth or seventh word. And if it's something that's a bit involved, you start getting quite frustrated. So ultimately, with a sound system, you want to sort of have critical distance as far up that room as you can. Ideally, you want it all the way to the back. And then really ideally, you want to do it with just a couple of boxes. You don't want to interfere with sight lines. You want everybody in the room to hear the same thing. You want to be mixing, whoever is at the mixing position needs to hear it exactly the same as everyone else in the room is hearing it. So if you're making an adjustment there, you are making a representative adjustment to something everyone else is going to hear. Now, you also have, all the stuff about comb filters and all the other issues with an array. Now, what we did was we figured the world didn't really need another line array, but what it did need was uniform coverage. Now, we decided to try and treat the problem of intelligibility as an energy distribution problem, not a sound audio quality problem. Because as soon as you talk audio sound quality, you're in the anechoic chamber, you're doing all your measurements, you're putting it up in a nice optimum room, and you're playing music that you're familiar with, or you're getting someone to speak. You're in an optimum environment with a sound system that you have set up, put in the right place, and it's got all the stuff. When does that happen in the real world? Probably never. If we go back to our architect, we're back to our architect who's made no provision for your sound system. It's where it has to be hung, where you've found something strong enough, it's in the wrong place, because the big heavy PA that weighed 180 kilos or 200 kilos it's too heavy to go in this spot, so it's got to go in that spot. And then you've got to have fill speakers, and then you've got to have outfills. It all just gets messy. And then you've got to hope it's been installed properly, and then you've got to hope that someone switches it all on and that nobody's pushed a button. That's why we've avoided processors as much as possible, because that's the other thing people mess up is the electronics. So they just can't, I call it sticky finger syndrome. So what we did is we started thinking about as an energy distribution problem. And we looked at point source distribution. If we could deal with the problems of the lobing and the tangential waves, and if we could keep the energy focused, we could control where the sound went without having to use electronics in an arrayable system that could be just bolted together by anybody and pretty much installed by a Sparky that would kind of work, that lowered the the potential for reflections in a room, we would be somewhere. So what we did was we hired a Frenchman, which is what you do in this situation, and we hired a Frenchman from Nexo. And he came out to Australia and we posed this problem. Now, he had been the measurement guy at Nexo. His name's Guillaume Boda. And he had, as much as he was he was an all right designer, but he had measured everything. And he'd worked with Francois Defrague and Eric Vincenot, who designed the geosystem, and though he was in every meeting they had. So we got him out, and what we wanted to... You might remember years and years ago, Altec used to have a theatre system with this massive horn on it that had this rather chunky looking early version of a CD horn, and it was, an asymmetrical horn designed to go into the good old A7 type bin that would be on either side. And they had this concept of a narrow beam at the top and a wider beam at the bottom. And when we looked at it, we thought, well, that's what we should do. And Nexo had one, they had a box called a PS15, which was a little single-use, single-box point source kind of thing that was very popular as a foldback monitor and had a number of advantages. But they had to run it with a processor, because it very quickly occurred to us when we started doing the maths that if you're going to have an asymmetrical waveguide, if you bolt a normal driver on that, all your path lengths are different. And consequently, without a processor of some kind, it's going to sound different everywhere on the horn, have a massive phase shift and have all sorts of issues, you see. So we looked at ways we could achieve that result, and but rather than do it as a single box, as Nexo had done, we wanted to have a narrower coverage, develop a new type of waveguide where we could do this without having to use a processor. Now, we tested every driver. Guillaume, we spent probably about 9 months testing and got pretty much nowhere. The first 9 months, nothing worked. We then went and, we were building 3D, because by then rapid prototyping was not as expensive. There was a rapid prototyping machine in Australia, so we started rapid prototyping phase plugs. We started looking at ways of shaping the horn and matching it to a type of phase plug that would... But then the problem is, of course, we actually came up with one that would work. We called it the pufferfish, a weird-looking thing, because it looked like a pufferfish. But the problem is that you could make it on a plastic rapid prototyping machine, and that was it. There's no way we could manufacture these things. And we weren't quite ready to wait for the next 5 or 6 years before someone could make a rapid prototype something like that could be made in production. And then fortunately, now nobody associates Celestion with innovative high-frequency design research, and neither did we. But we ran into a guy who knew someone who was an engineer at Celestion who had developed a particular type of phase plug system and a way of making it. And we had a look at that, and it was a different looking diaphragm. It was quite different. It profoundly looked like it would not work, but I'd seen other things that looked like they wouldn't work that did. So we got on board with that, and we sent him our design and said, look, can we optimise it to work with this flare, which almost worked, but just needed a bit of help in at the source end. So he developed a product for us. Now, what we ended up with, and that's a pretty tacky picture, but our concept was to have an asymmetrical coverage that we could array. And what we ended up with is this system. Now, how it works is, yes, you've got, we stuck with at the bottom of the flare. If I go back to, say, this one, if you have a look here, it's a bit of a distorted picture, but anyway, 30 degrees at the top, 60 degrees at the bottom, and it's 15 degrees up and 45 degrees down. Now, the idea was that if you stand right in front of that, it just about cuts your head off because you cop a beam. There's a lot of energy in the top 25% of that horn flare. But when it's hanging in the air, that just pings straight over everybody's head, and that energy wave then opens out at you as you head up the room. And what we were trying to achieve is, as you walk away from the box, your receipt of the high energy, the high frequency energy, stays basically the same. So as you go along, theoretically you're going to have a different frequency response as you get away from the box. But once you put it in a room, bearing in mind that, okay, there's not a mountainous amount twanging off the walls, but because we don't have any directivity in the bass driver, and we're crossing this horn over at about 900 hertz, we were trying to put the asymmetrical control in the vocal range, and that the bass woolly crap that bounces around the room, so long as you're getting more of that intelligible HF and mid-range than the woolly stuff that's twanging off the walls, you will retain intelligibility. And if you were to plot it, nothing to get excited about. But coming back to our Alcon test, if you plotted it using a RASTI system, it'd be all right. But as soon as you did a real test with someone standing there reading the phone book to you, you'd be up there at 97, 98% in a real world environment. Now, someone would then turn and say, but what about the tangential effects? Let's have a look at one here, for instance. What about the tangential interference? Well, what's worse with the tangential interference is when you have a whole row, you have a whole quantity of energy coming from a line this long, which the horn in these is quite big. It's actually almost something like a third of the box, nearly half the box. So if that was a straight horn and you were putting them together in a row, you would have that big Christmas tree lobe effect. But once you have a changing wave where you've got this at the top and that at the bottom, especially if you spread them out a bit, the actual interference is a great deal less. And instead of it being a lobe, what you have is like a cheese grater. Imagine if you put a light in a cheese grate, you have little dots everywhere. Well, what you have is a little cloud of dots along the front, and the cloud of dots diminishes as you get up the room. If you throw far enough, it'll eventually start to intersect again, and you get a bit more of a cloud of dots. But what we've found is that you can't hear a cloud of dots, but you can hear the Christmas tree. So that was pretty much the approach that we took. And the other idea with it is that with this kind of system, we designed it basically to work in a room. We originally were trying to do 600 people rooms. We've actually found that it's worked that well that with a triple array, well, it's like this one back here, that's actually a 1,200 people room that has a row of 18-inch subs, which I haven't put in this picture because it looks obscene. They have this nice little tidy miniature-looking PA hanging in this great big box. This is a Korean church with that's essentially a factory, a big square box with nothing on the back wall to stop a massive reflection. But when you're sitting out there where the crowd are, you can't hear it. You hear it on the stage, but you don't hear it out in the room. Now, then they decided to hang a row of subs because they'd done this funky thing at the start, coming up the stage, this cascading stair, which kind of looked all right, if you don't mind the broken ankle you'd get if you tried to walk down it. And then had this tiny little PA and then just hung a massive row of subs on the roof, which I just couldn't work that out. But anyway, what we were trying to achieve was something that was very simple for people to use, that could be used with or without a processor, and that essentially could be used as a 1, 2 or 3 box system. The other thing we had to do was make them light. These boxes weigh 16 kilos. You can see this is another one that's going up in a Salvation Army church. One guy's holding up the array while the other one's chaining it up. The scary part of that picture, which you can't really see there, is number one, the Bunnings chain. This is a video guy's putting it up. Bunnings chain, the Bunnings shackles, that's bad enough. And on the other side of that ceiling tile is a piece of 2x4 holding it all up. Just horrendous. But anyway, that's how I was to get the video guys to put up the PA. But so anyway, despite the potential for the comb filtering and the lobing and all the other stuff, I think we get away with it. Now, what I'm going to do is I'm going to run a bit of a test. Now, the whole point here is this is a good example of the type of places we make sound systems for. It's like about here upwards to about 1,200 people. Now, the whole point of this is, as I said, when this was designed, this stage was going to be back here. So it is hanging a little bit back, but that's kind of good because it means that it actually will degrade its performance a little bit as far as the stage is concerned. But it's a great opportunity. What I'm going to do is we're going to play some speech. Now, I've got 2 tests here. I've got some recorded speech, and what I was going to do was play it, and you're welcome to walk around, but you can just hear it even just sitting there if you like. We're going to simulate reverb just to give you the effect of how reverb destroys consonant sound and makes something a bit unintelligible. Alan, do you want to run that? I've got just a passage out of a theatrical play. It's a bit hard to understand at the start, but then we're going to run it, and then we'll run it again without the reverb. And you're welcome to walk around and have a listen. Do you want to give it a try, Alan? Pity you can't see the vision that goes with this, because it's...
Is this the diagram which I see before me?
You're well and truly past critical distance here.
Let me clutch it. I hardly not. Yes, I see thee still. I don't know how fatal vision sense of the feeling as to sight. Or art thou but a dagger of the mind, a false creation, proceeding from the heat of oppressive brain? I see thee yet. Thou marshalest me the way that I was going, and such an instrument I was to use.
Okay, Alan, do you want to run it again, but this time get rid of the reverb? Actually, do you want to try the... Yeah, no, just run the same one. It's not a test if we do something different. Yeah, just pull the reverb out and run it again, if you can. Thanks. Now, I'm pretty up for, as I said, there's a wireless mic there if anyone wants to ask any questions.
Is this a diagram which I see before me? The handle toward my hand.
I'd be interested to know if anyone can hear any lobes or find a spot where it's not working.
I hardly not. Yes, I see thee still. I don't know how fatal vision sense of the feeling as to sight. Or art thou but a dagger of the mind, a false creation, proceeding from the heat how marshals me the way that I was going, and such an instrument I was to use. My eyes are made fools of the other senses, or worth all the rest.
Try another one. See if you recognise this one.
Friends, Romans, country, lend me your ears. I come to bury Caesar, not to praise him. The evil that men do lives after them. The good is oft interred with their bones. So let it be with Caesar. The noble Brutus that told you Caesar was ambitious. If it were so, it was a grievous fault.
So you'll see that the
quality of mercy is not strained. It droppeth as the gentle rain from heaven upon the place beneath.
So the whole idea with the asymmetrical projection is it does throw down as well as out. And having the energy dissipated over a much wider area means that essentially, even though I'm pretty much in line with the boxes here, you can walk under it even with a lapel mic, and it's pretty reluctant to feed back because there's no hot zone. Because the hot zone that there is, and there is one, is actually beaming over people's heads and opening out. Now that's the concept. We've developed this also to use on a number of other products for sort of specialist type applications. But anyway, look, that's as I'm not doing this. This is not trying to sell Quest boxes here. But what I'm pointing out is that what our design approach for this has been to look at this as an acoustic energy management problem, and by approaching it from that direction, what it's meant is a whole lot of the sound spectral problems basically went away, because at the end of it, we actually got a product that we were quite happy with. It sounded... Because what we wanted to do was just duplicate... We're not trying to improve anything. We're just trying to get the voice to sound like it sounds. Now, in a real line array environment and in a bigger room, a line array will put an image right in your face. But that's if it's working as a line array, if it's been set up correctly, if all the angles are right, and if it's one of the few brands, there's a few more now that are pretty much creating a line array, certainly in the mid-range. So, you get the D&B line array. The Germans have been clever with D&B because they haven't actually invented a whole lot, but they've just taken the existing known data and, as only Germans can, meticulously delivered it. So, I've heard some D&B line arrays that I thought were really good. But once again, to do this kind of room with that kind of system, it's still going to twang off the walls and ceiling because it's just going to hit that back wall and bounce everywhere. It doesn't really have... It has directivity like a single box, which is what line array people are trying to do. They're trying to create a multiplicity of boxes to behave like a multiplicity of elements to behave like one element. And that's what they do. A really good line array will do that. And in a big, long shoebox room, that's what you want. And a high ceiling. With a high ceiling, you want that. You're still going to have to treat the room a bit, but in most cases, if it's installed properly, it'll work really well. But our concept was really to look at these kind of venues in a real-world environment and make something that gave you a very uniform speech coverage in a wide kind of environment. Now, if you hang the 3-box array, you get pretty much the same result in a wider room. But anyway, look, I welcome any comments. If anyone has anything to suggest in the future or any ideas, we'd be pretty interested to hear what people think. And now I shall get off.
Perhaps
Thank
I
you.
can start some questions.
Sure.
Are these acoustically or electronically equalised?
Well, what we did was we actually had a little machine called a Klippel. Now, in this, so the Klippel was very involved in the design of the components, because we found to actually create the products that we wanted, we had to really go back to and redesign the component. Now, there is a bit of EQ going on here. In the back room, there is a silica processor. There's a bit of tweakerama in it, but there's not actually much. What surprised me, when they installed this, they rang me and said, "Oh, can you come down and help us EQ the PA?" Well, I basically came down, had a listen to it, and walked out the back and thought, just twiddled some knobs. It just looked like I was doing something, you see. And then ended up going, I can't tell if that's any better or not, so I just put it back the way it was, because the guy here who'd done the install, who was pretty switched on, he's actually a great audio guy, but even then he came out, I said, "You did a great job." He said, "Well, actually I didn't do much. I thought you might have found something for me to do." I said, "No." So yeah, there's very little on it, really. There's not much. There's not. We didn't want to, because we knew that, look, our biggest market at places like India and Africa and the Middle East. We do a lot in Asia as well. So we just wanted to make this so if you can find the on button, it'll kind of work.
Passive and powered versions?
No, look, we've been talking about doing a powered version. We sort of built a few and then we didn't end up doing it. Look, we are, for installed sound, passive is probably still more practical, though just due to the nature of the market, powered will become more common, and there are a number of reasons to do it as well.
Questions?
Right, why are the speakers hole there?
Yep.
Why did you choose that spot to put them?
Well, that was really because when that fixing point was put in, it was a concrete floor and a bare room, walls. There wasn't even any ceiling. The thing was, they rang me up and said, "Where do we put the PA?" I said, "Wherever you like, just as long as it doesn't obstruct the projectors." And so, I mean, I probably would have liked it a bit further forward and maybe in a little bit, but the other thing is that one of the drawbacks with this kind of box configuration, especially when you put up three of them, the back of the box is forming a little bit of a parabolic surface. So anything that comes off the back of the box is going to actually hit a back wall and send a lobe out. And so inside the box, that's really thick and dense plywood, and the amount of stuffing that's in that box is substantial. Plus there's steel bands that all run around the inside of it as well, because there's 9 rigging points on it too. So we had to make it so to try and minimise resonances, because, and even then, on this stage, it's a little bit ugly because there's a bit of a little resonance that twangs around the back that's in that hot zone in lectern mics. So there's some pretty ugly EQ on this microphone, but it's relatively cheap lectern mic too. So, I mean, you're not going to fix, even when I've seen people that have had complex systems that potentially could perform better than this, they generally don't, because they don't survive the installation process very well. Any other question you'd like to ask?
Which were the particular line arrays that you think are the good ones?
Well, look at it this way. I mean, ultimately, anything that sounds good is good. I mean, you can get a bit carried away with the tech speak on them. But if I get to a line array and I can grab the bottom box and push and feel any play at all, that's a problem, because you've got to have no space between the elements. They've got to be really tightly locked, because it's back down to basic physics. You've got path lengths, and as soon as, for the Nexo Geo, for that to be so precise that if you were half a degree out, the whole wave collapsed, told me that precision in the system is very important. When I looked at the DNB, I thought, that's not a line array, but it sounded great. So whatever they've done worked. Adamson, DV-DOS, made really well. Maya Sound have put out papers that tries to refute what the Nexo papers were. And you get to the point where you get into a bit of a feedback loop of technobabble. And I have waded through them all. I get a bit sus when I see a paper that is either maths for days, like formulas, or no maths at all. There's got to be a pretty decent qualification in the physics of what's going on. It's like when you go to China. You go to a Chinese manufacturer and there's manufacturers that make line arrays. And what happens is you go there and they've got a big anechoic chamber and they've got a clipple and they've got audio precision and they've got an end, they've got stuff for days. And there's guys there in white coats. And Michael Barabbas would know this one for sure. You walk in there and he pretty quickly susses they haven't got a clue. And it's all for show. It's just all there. And they sit there and they print out graphs and they've probably got about 10% of it to work. But unless you've got all the right modules and the modules express what you're doing, it's fake. And there's another company in Germany called Kardenbach. They make a real one. You'll never probably see that one here. Realistically, if I walk in and it sounds good and I can understand what's being said, I go, that's good PA. But in real terms, there were only 3 that I knew of that were rigid edge, and I'm a bit out of touch now because I've sort of lost interest in them a little bit because we're never going to make one. So,
okay, no more questions?
There's one more over here.
Just a quick question.
Yep.
Obviously, acoustically, this room is really good and the great boxes sound really, really good. Is there a comparison or another venue where you've installed a similar system that might be good to...
Well, there's only a few places. Funny enough, I don't actually know where they all are. I turn up somewhere and I might see one because we're the manufacturer, we're not actually the distributor. So I get people ringing me up, but I don't actually necessarily know where they all are. But I could certainly find out. The interesting thing here is the guy who did the install was a real sound guy, and the guy project managing was listening. And this is a good room, and it's also the kind of room that this system was designed for. This is on the smaller end. You can actually go a bit bigger with this array, and then you can go to a different configuration. It'll take you out to a larger one. Whenever I've heard them, I've generally walked in and thought, I can understand what's being said. And as I said, I'm a little bit deaf, so I haven't heard any that I've thought I've had to come back and fix. I've heard some where I thought I wouldn't mind coming back and getting them to rehang the boxes a little bit, but I'm probably being a bit pedantic. Whereas, I've gone in and I've got a lot of time for Nexo, and I've gone in and half the Nexo installs I've seen I thought were horrendous. I thought they just wasted their money. Spent $150,000 on a PA and it's rubbish. And yet I've known what that PA could do. And it gets back to what's the rigging accessories? How is it easy to install? Nexo don't have a great rigging accessory option, or didn't. They're getting better now. But when you get a piece of steel that's to hang a box and they want $4,500 for it, you go, guys, what are you on? They're just going to make their own and it's not going to work properly. So you get back to practical realities as well with a lot of this. The plate to make that, it's made at Mitcham Laser. You can put it together with a screwdriver and it just doesn't cost much. So that kind of thing, I think there's a bit of Aussie design approach, even though it was designed by a Frenchman. He did have a whole lot of Aussies standing over him when he did that. And Guillaume wasn't the only person in on this. There's a few fingers in that pie, because we developed a whole system. There's bits of this in practically everything we make now has got some element of this in it. So.
Okay, safe. It's not often that we get a chance to have somebody who's gone through the whole process and created from scratch a product that, to me, works extremely well and targets a market accurately. So well done to Frank and his team. I think we thank him tonight.